Hello, everyone. Today, I'll present you a work related to virtual interrupts on the RISC-V architecture. Virtual interrupts are an integral component of a virtualization solution. However, since the capability of directly delivering interrupts from pass-through devices to a VM, we have not seen much development in this venue. Here, we'd like to take the opportunity of the emerging RISC-V architecture to introduce some new ideas to keep improve virtual interrupts. In this presentation, I'll first provide some background information on how the virtual interrupts are processed on the current RISC-V KVM architecture as to motivate our proposed improvements. Next, I'll talk about more detail about our improvement, which includes the design of a virtualization-aware interrupt controller and direct delivery of virtual interrupts to a vCPU. Next, I'll show you the detailed implementation in KVM to handle the various kinds of virtual interrupts and vCPU state changes. I'll also show you some performance results. Lastly, I'll briefly talk about some future work and directions. Let's move on to the background and motivation. The current hypervisor extension on RISC-V does not include any support for accelerating virtual interrupts. All virtual interrupts are implemented on a trap and emulated approach. There are three types of virtual interrupts that are of concern, corresponding to three types of physical interrupts. There are virtual timer interrupt, virtual supervisor software generated interrupt, and virtual supervisor external interrupt. The current flow of the virtual timer interrupt is shown here. Whenever the VM kernel needs to set up the timer for a timer interrupt, it needs to trap to the KVM, which utilizes the HR timer and the timer driver, which finally traps the machine mode to set up the physical timer. On an interrupt, the heart is switched to machine mode first. The OpenSPI then injects timer interrupt to the HM mode host kernel, which then injects the timer interrupt to the guest kernel. The entire process includes multiple traps and components. Many cycles are spent on emulation of the timer interrupt to the guest. The virtual software generated interrupt is shown here. To send the virtual software generated interrupt, the guest VM needs to call the emulated SPI by the KVM, which causes a trap to the host. The host saves the interrupt for the other vCPU and notifies the heart that the other vCPU is running on. To perform the notification, the host needs to call the real SPI, which causes another trap to machine mode. When the machine mode interrupt arrives at the other heart, the heart first switches to machine mode. The OpenSPI injects a software interrupt to the host kernel. Then the host kernel realizes that there's a saved software interrupt for the guest. Injects this interrupt to the guest when resuming the guest. We can see that virtual software interrupt also introduces a number of traps, resulting in the same situation as virtual timer interrupt. On the current KVM on RISC-V, to send the interrupt by the emulated virtual device in QEMU, the steps involves firstly to perform necessary emulation of the PLIC. Next, to notify the guest VM, a trap to host kernel is needed by the PLIC. KVM module in the host kernel next saves the interrupt info for the vCPU and uses the host software generated interrupt to notify the heart on which the vCPU is executing. The vCPU traps and quickly resumes the execution. It picks up the interrupt during the resumption. We see that again, a number of traps are needed in this process. During the handling of interrupt from the virtual devices, again, a number of traps are incurred. The main reason is that the MMIO access to the emulated PLIC causes traps to the host. There are further switches in the host when the PLIC emulation code in user space interact with the host kernel. The MMIO is needed to at least acknowledge the pending interrupt and to signal end of interrupt handling, which involves at least two traps. So we notice that all the processing of interrupts involves a number of traps. Meanwhile, other architectures such as x86 and ARM have been providing direct delivery of certain kind of virtual interrupt to the vCPU for a while. So direct delivery of virtual interrupts avoids excessive traps, reducing overhead and improving the overall performance. The question is, can we have something like that for RISC-V? From that, let's move on to our work that on the RISC-V actually. So we extended the interrupt controller on the current RISC-V architecture to support direct delivery of all kinds of virtual interrupts, including virtual timer interrupt, virtual software generated interrupt, and virtual supervisor external interrupt. We have also implemented necessary support on the KVM for KVM to validate the functional design of the extended interrupt controller. Note that our extensions idea are not dependent on a particular interrupt controller and can be adapted to future interrupt controller as needed. The existing interrupt controller on RISC-V consists of two parts, the CLINT and the PLIC. The CLINT mainly contains a local timer CSR called M-time CMP. The PLIC acts as the routing unit, so to speak, for external interrupts and software-generated interrupts. It contains the various controls and status bits for the interrupt sources. I'll skip the details of these. Please refer to the specs if you're interested. We have extended the CLINT and the PLIC with a set of CSR to support direct delivery of virtual interrupts. For each type of virtual interrupts, we provide CSRs according to the functional requirement of the virtual interrupt. For example, for timer interrupt, we provide a CSR for VS mode and VHS mode that act as the dedicated clock event source, respectively. The CSRs can be accessed directly from the mode they are intended for without trapping. The guest VM can directly set the timer interrupt with VS time CMP, for example. It does not need to trap to the host. All other CSRs follow the same idea. We extended the PLIC to handle virtual interrupts that are not local, which are the virtual software generated interrupts and the external interrupts. These new registers contain structures that are used for routing virtual interrupts while considering the host scheduling decisions. For example, for each heart X, we provide the corresponding IF-map X register. The IF-map register holds the VMID and vHeart ID pair that indicates the identity of a vCPU that is currently running on the physical heart X. When the PLIC needs to deliver a virtual software generated interrupt, it looks up all the IF-map registers in parallel to locate the target vCPU. If any of these slots matches, the PLIC knows that the target vCPU is on the heart that corresponds to the slot. The advantage of this design is that instead of contention on the single share resources such as global table or certain kind of command queue, each thread only writes to its own slots without taking any locks. The hardware later can perform the lookup in parallel. The other registers are designed with this same idea. To directly deliver virtual interrupts, the CLINT needs to be able to directly set the pending bits for the virtual interrupts. Currently, such pending bits are only set by host software. We changed that so that when V equals 1, the guest receives an interrupt directly. The V bit is RISC-V nomenclature that whether the heart is running a vCPU. To minimize the possible delay, we also consider delivering the interrupts when V equals 0. When a virtual interrupt arrived on a certain heart when V equals 0, the host still handles it. In this case, the virtual interrupt goes along the same handling path as the existing approach. So our design is as good as the existing approach in the slow path. Note that also conceptually this needs differentiation between the interrupt from the same source but handled by different entities. Because even if the host claimed the virtual interrupt, the handling does not finish. The virtual interrupt should still remain pending for the guest. So to differentiate the pending states of the same virtual interrupt for the hypervisor and the guest, we need to introduce additional bits. Different types of interrupts need to be treated differently. We don't need one for the virtual timer interrupt because the hypervisor doesn't really claim a virtual timer interrupt since it's level triggered. Having separated HIP the VSTIP bit and VSIP the STIP bit does not really make sense. Eventually, the timer will clear any pending bits once the value inside is updated to represent future time. We do not need to separate and we do need to separate the enable bits though, the VSIE, the STIE, and is no longer an alias of the HIE, the VSTIE. We introduced additional bits for VSSI by separating the VSIP.SSIP bit from the alias relation with HIP.VSSIP bit. We also need to separate the enable bits. We use for virtual supervisor external interrupt, we use another notification interrupt to represent the host interrupt. So the separation is completed with the pending bit for that notification interrupt. To support the above interrupt controller extension, the KVM's main task is to handle the interrupt when V equals 0 and to maintain a consistent interrupt context for each vCPU. The vCPUs in KVM essentially is in one of the three states shown in this state transition diagram. KVM's main task concentrates on the right portion. When the vCPU is in paused and scheduled off state, the KVM handles the virtual interrupts, saving them for injection if necessary. When the vCPU transits between the two states, the KVM performs necessary context maintenance in KVM vCPU put and KVM vCPU load functions. The reason for the host to handle the virtual interrupt for the guest is that if the vCPU was not scheduled off, it's just paused, the interrupt controller will still regard the heart as having the vCPU running because the update of the IF-map X register happens in vCPU put, KVM vCPU put and KVM vCPU load. Then the virtual interrupt will still arrive, but the vCPU is not executing. Next, we will show how KVM performs these tasks for each kind of virtual interrupts. That brings us to the actual trapless virtual interrupt. For virtual timer interrupt, to set a timer, the guest writes to the VS time CMP CSR via the alias S time CMP to set the timer. The host writes directly to the VS time CMP to switch the vCPU context. When a timer interrupt fires, if the vCPU is in running state, V equals 1, so HIP.VSTIP is set, the guest handles it directly. In pause state, V equals 0, HIP.VSTIP is still set, however, the host handled it this time. The host does this to allow a necessary priority adjustment for scheduling, for example. In the scheduled off state, the host tracks the vCPU's timer using HR timer, which is the same as the existing approach. So no timer virtual interrupt is fired. During the vCPU's state transitions, the KVM needs to maintain consistencies. So during the transition from the running state to the pause state, the KVM saves the state to the VSEI CSR so that if the vCPU enters the pause state because it executed WFI instruction, the host needs an updated view to whether the guest has enabled interrupt so that it can bring the vCPU out of the vCPU block function later when the interrupt is intended for the guest. For the transition between the pause state and scheduled off states, the KVM needs to save the value of the VS time CMP CSR and utilize the host HR timer facility to track the timers set by the guest. As shown in these lines on the slides. The host needs to temporarily disable its own handling of VS mode virtual timer interrupt because if at any moment the value being saved or restored happens to be in the past, the host needs to avoid double handling of the same timer interrupt again. This is because we still need to maintain the level trigger semantics of timer interrupt, the same as defined on the physical platform. So with the extended interrupt controller and the KVM support, now the virtual timer interrupt can be directly delivered to the VM kernel when the vCPU is running. When the vCPU is paused, the interrupt is delivered to the host, which immediately injects it to the vCPU. When the vCPU is scheduled off, the host utilizes the HR timer to track the virtual timers. The HR timer uses the new timer dedicated for the HS mode, avoiding traps to the machine mode. So that's for virtual timer interrupt. For virtual supervisor software generated interrupt, when a guest vCPU needs to send a software-generated interrupt for another vCPU, it writes to the sgen IPI CSR to do so. It does so and specify the target vCPU ID that's intended to receive the virtual software-generated interrupt. After the write, the PLIC received the target vCPU ID, so it looks up all the IF map registers, whether it is one that contains a specified vCPU ID. If found, it delivers the VSSI to the heart with the, oops, to the heart with M heart value N, which is the N slot that contains the matching vCPU ID. The vCPU can be either in running state or in pause state. If it's running, the guest take the interrupt directly and handles it. If the vCPU is paused, the host takes the interrupt and injects it to the vCPU. If there is no such a slot that contains the specified vCPU ID, a notification interrupt is delivered to any host heart for later injection. The vCPU now must be in the scheduled off state. The KVM job is also to maintain context for virtual software generated interrupts during the same state transition. When the vCPU transits between the running state and the pause state, the KVM synchronizes the saved pending state for the VSSI and the hardware VSIP register. Recall that we separated the pending bits for the guest and the host, unlike the virtual timer interrupts. When the vCPU is in pause state, the host handles the VSSI that receives because the PLIC thinks that the target vCPU is still running on a particular heart. When the host schedules off a vCPU or schedules on a vCPU, it updates the corresponding IFMAP register. When the target vCPU is scheduled off, the PLIC sends a notification interrupt to the heart so that the host can wake up the target vCPU and resume its execution. With the extension on the interrupt controller and KVM support, now the VSSI can be directly delivered to the VM kernel when the vCPU is running, avoiding traps to the host. When the vCPU is not currently running, the host receives the interrupt and injects it to the vCPU, same as the current solution. Similarly, for virtual supervisor external interrupt, when the virtual machine is created, the host allocates a piece of memory for pending bits of the external interrupts for the VM. When the emulated external device needs to send a virtual supervisor external interrupt to the guest, it writes the new UGen VSEI CSR to send the external device interrupt to the guest. It writes the VM ID and the interrupt number into the register so that the PLIC receives this. It looks up the virtual interrupt affinity tables pointed to by the V table base N registers and locate the vCPU that this virtual interrupt should be delivered to. Next, the PLIC performs similar tasks when it's looking for a particular vCPU for the software generated interrupt because this kind of interrupt also resembles the software generated interrupt because they are between, it happens between hearts. So the PLIC looks up the IFMAP registers to see if there's a matching vCPU ID. If there is, it delivers to the virtual interrupt to that particular heart. If the vCPU is running, it takes the interrupt directly. If it's not, the host takes the interrupt and injects an SEI to the vCPU. If not found, a notification interrupt is delivered to the host. After the guest receives the external interrupt, it needs to handle it. There are at least 2 steps during the handling of the interrupt. So for guest to claim and to signal the end of interrupt processing, the guest just directly read from and write to the VS claim register to claim and signal it. Reading and writing to this particular register does not cause traps to the host in our design. So similar to the other virtual interrupts, the KVM saves and restores the HIP CSR when the vCPU transits between the running and pause state. When in pause state, the host handles the VSEI that it receives because the PLIC thinks that the target vCPU is still running on the heart. The PLIC reuses the same IF map register to decide if a target vCPU is executing on any heart. When the vCPU is scheduled on and off, the host needs to maintain the pending bits for that particular VM, like this. When the vCPU is in scheduled off state, the host handles any notification interrupt for VSEIs and that targets the scheduled off vCPU. So with this extension and corresponding KVM support, the VSEI can be directly delivered to the VM kernel when the vCPU is in the running state, as shown in this diagram. When the vCPU is not running, the host handles the interrupt and injects them to the vCPU in a similar fashion as VSSI. On the processing and acknowledging side, the claiming and signaling end of interrupt also happens without trapping. The VM kernel that directly reads and writes a vclaim CSR, which updates the states accordingly. Let's move on to our implementational results. We have implemented the above interrupt extensions in RISC-V QEMU version 5, which provides an emulated RISC-V environment with a hypervisor extension. We're using QEMU because right now there have been no hardware that RISC-V hardware that contains hypervisor extension, so we got no choice. Um, we have also implemented necessary KVM support. On this KVM support, we ran benchmarks that can be compiled and ran in the emulator with reasonable support and obtain some performance results. Mainly, we are able to compile around Redis and Unix bench. And here are the results. This benchmark shows the performance boost in Redis obtained by adopting the extension for the virtual timer interrupt. With one vCPU and the virtual timer interrupt extension, we observed around 60% to 70% of performance boost compared to the original solution. The gain mainly comes from the elimination of the traps to update the timer and to deliver the interrupts. Similar results are observed for Unix bench. This figure shows the performance boost in Redis with both the virtual timer extension and the VSSI extension. With two vCPUs, we observe around 50% performance gain compared to the original SPI-based interrupts. The performance gain, again, also comes from the elimination of the excessive traps to the host and to various nodes in the host. For VSEI, we used ping to the virtual machines from the host and measure the latency. With our extension, the latency is reduced by 11% on average. The gain also comes from elimination of traps due to I/O operations. The traps are like we ping the machine 100,000 times and we observe traps reduction due to MMIO by around 300,000 times. This number is expected because the current flow of IO handling do cause like around 3 traps per handling, 1 interrupt. So we think these results here are strong indication that the extension can reduce the performance cost due to frequent traps. Although actually when implementing the hardware, the magnitude of the numbers may change because we are still using an emulated environment. So for the future, we like to continue to explore along the direction to include support for pass-through devices, which means we need an IOMMU in the first place. We still need to furnish our extension with more details with practical implementations, such as priority controls, etc., etc. We will also like to seek to integrate our extension with future RISC-V interrupt controllers as well as validating our ideas with more hypervisors. With that, I end my presentation and thank you for your attention.